So welcome to Soft Earth Chalk Talk number 2. I sent it around, but the title is Everything is Threshold. The other part is threshold is everything. Okay? Now, as I told you, I don't like to tell you in the beginning what I'm going to be talking about. I like there to be a little bit of a mystery. I know, Paula wants me to tell you, so I decided not to. But what I want to do is unspool the story of what I'm talking about in terms of why everything, at least on the soft earth, is threshold. And if everything is threshold, then understanding threshold is everything, right? That's what the second part is. So I'm going to start where I usually do, right? There's still geophysics in this class. And if you're uninitiated, the geophysics great unifying theory, the kind of premise that brings together all of geophysics and makes everyone sort of hold it up as a success is plate tectonics, right? You kind of can't get away from plate tectonics. For us, the important bit I want you to understand is the way in which plate tectonics creates a critical planet, kind of from the get-go. All right, so I'm going to do a dangerous thing and try to like draw the planet Earth in a kind of perspective view. You know, this is not something I'm very good at, right? But, you know, and so if you have this idea, remember that we have the planet in these layers, right? And so we have the core in the middle that we don't really care about. We have the mantle, which I'll draw in green because it's mostly olivine, which is green-ish, right? But the main thing, first of all, that we care about, right, is that we have this mantle convection happening because there's a thermal gradient here. It's hot in the middle. We talked about the rock rising at about 1 centimeter a year if you want an order of magnitude. And when that hot rock, which is rising, gets to the top, brushing up against the crust, then it's going to drive the crust. It's pushing it, right? And so we have the situation where the crust is getting driven from below by drag. It's a fluid drag in some sense because this is convecting like a fluid, but remember that it's solid like rock. And the other thing, though, to think about is that this now is the crust that I'm drawing here, right? That the crust is cracked, right? So this is a brittle shell. The crust is more brittle than the mantle. The mantle is flowing and behaving kind of fluidly to ductily, and the surface is this more brittle shell, right? And it's cracked. So the tectonic plates, the way that I like to say it to people is imagine that you took a dish or a plate and you smashed it so that it was shattered. And then you just drove it with a fluid from below, right? So the plates are all crowded together, right? And they're filling up all space, but they're being pushed around. Some of them are being pushed together, right? In other places, they're sliding past each other, right? And in other places, the plates are getting ripped apart, right? So there's places where plates are coming together. There's places where they're getting ripped apart. This causes the plates to tilt up. This causes the plates to rotate. All kinds of complicated things happen. But what I want to do is zoom in on a convergent plate boundary. Okay, so when I say a convergent plate boundary, I mean where the plates are coming and smashing together, right? And so when two of these plates come and smash together, we're drawing from the side. Basically, what's happening, right, is that here's our convergent plates again. We're drawing them from the side. These two plates come together. One rides up over the other, and the other subducts, right? So this thing that's going on here is the two plates are going together. The heavier one pops down and it sinks, right? The other one pops up and overrides. But remember also, we talked about last time, this rock is crumpling as this is happening, right? So this rock is smashing into this other one, getting stuck and crumpled. And what happens is, right, it builds up a mountain range, right? And so we're building this mountain range by rock that is getting continuously fed in this conveyor belt, right? So you can imagine at some time 0, where there is no mountain range, this plate starts colliding and it piles it up a bit, piles it up a bit, and it keeps piling up. And at some point, the mountain gets critically steep. Now, beyond that point, the mountain can grow if mass is being delivered to it, but the mountain will maintain this critical slope, okay? The way to understand this is to think something like a simpler picture that maybe you're familiar with, maybe you're not, but I'm going to do my bad job of drawing a tractor, okay? So imagine that this is a tractor here with a plow in the front, and this tractor is driving over soil, right? So we'll draw the little farmer right here, holding a steering wheel, right? So this tractor is driving. I'll draw a little fender on it. Maybe that makes it look more like a tractor, right? So this tractor is driving and plowing up the soil, right? Pushing up the soil. And as the tractor drives, what you're going to see happen, right? You're plowing up, and you build this pile up to the point that you have this critical wedge of material. And it's after this point where you build this critical wedge of material, this critical wedge of material is at a critical angle at which this material avalanches, and it's getting pushed along the foundation, right? And so we have this idea when we're plowing soil that in the beginning, we build up this critical wedge. But then when this critical wedge gets to some critical slope, that when we add more material to it, it just continuously collapses and it maintains that slope, right? So here with the mountains, in the beginning when you're adding mass, the mountain builds up to some slope. But at some point, you can add mass and the mountain can get bigger, but the slope doesn't get any steeper. Now, why doesn't that slope get any steeper? Part of the reason, if you said creep, part of the reason is that, right? It is true that the mountain, even made of rock, if you wait long enough, it does flow and relax a little bit, right? Even solid crustal rock will flow and relax a little bit. But there's another process which is much more effective than that, right? And so if you plow the mountain right here, right? So now I'll draw it in profile a little bit, right? So that we can see here. So if you build up a mountain range like this, what will happen eventually is that you will get to a critical angle that we'll call theta C. And at this critical angle, the rocks and the soil that they're breaking into are steep enough that what you will do, right, is cause a landslide. Right? And so remember, soil is just complicated sand, right? Soil has a critical angle at which it will begin to flow. We talked before about fluidizing soil, right? One way to fluidize soil, you can shake it, you can add water to it. The easiest way to do it is to just pile the soil up to a critical slope angle. And then beyond that, it's just going to collapse and avalanche on its own, right? Because it has a critical stress at which it's going to fluidize. So if you try to take this mountain and over-steepen it, increase the slope a little bit, these landslides will happen and they will bring the slope right back down, right? And so the mountains will essentially build up until they achieve this critical slope, right? So the critical condition is when the slope of the mountain is equal to the critical slope for landsliding. And that is basically the angle that you find most mountain ranges at, right? Of course, you can find exposed bedrock, or you can find slopes in places that are like 90 degrees, but if you have a soil mantled mountain, you will find them all at the critical angles, right? 30, 40 degrees, something like that, okay? This happens, right, at the point where there is a balance between the uplift rate and the erosion rate. So what do I mean by that? Right, we're still in this situation where the plates are coming together and they're adding mass to this mountain range. So that addition of mass is causing the mountain to lift up, right, at some rate. And the erosion of this material is being accomplished by landsliding, which is taking the material off the mountain and down into the valleys and into the rivers to be taken away, right? And so the mountains build to a critical condition where the angles are equal to the angle for landsliding. And the steady state situation that it sets up is where the erosion rate, which is being accomplished by landsliding, is balanced by the rate that new rock is basically being pushed up in the mountains, all right? So we have this idea that landsliding is essentially the dominant mechanism for erosion that's keeping mountains in their critical state. That is being created by plates that are crashing and smashing and get locked up into each other and then slip and move apart. The plate tectonic system is another system that's perched at critical. How do we know that? We know that plates are locked a lot of the time, and then we know that they slip catastrophically. They're all hovering around their threshold friction for slip, right? Basically, what both of these systems have in common is when you have a system with a strong threshold between a state of no motion and a state of failure or slip, and that system is being driven strongly, you've set up a condition where the system will be perched at that critical state, okay? And that's the theme of today. So there, Paulo, I gave the theme now of that's the idea that the rest is going to connect to. Now that sounds kind of simple, right? We have this simple idea that says, oh, these systems are critical. Figure out the threshold and you figure out the system. The thing I want to give us a hint for today is that systems perched at critical are not easy to understand, right? And so, just to give you an idea. So, let's look at, when I look at a typical mountain, it's got that landslide, it's got this landslide, it's got big landslides on it, it has landslides of all different sizes, right? So let's say that we just want to ask the mountain, what is the size distribution of landslides that we see on you, right? So we will describe the magnitude of landslides by their volume, okay? So we'll say that, you imagine you have a landslide that's, 10 cubic meters, that's a tiny one. You could have one that's 1 cubic kilometer, that's like the size of a whole mountain face, right? So you ask the question, what is the distribution of sizes of landslides? So if we ask the distribution, we ask the question, what's the distribution of a lot of different things? So you could ask a question, what's the distribution of temperature on October 2nd in Philadelphia, Pennsylvania, right? You can ask a question like that, and you would get a distribution that looks like this, right? So if this was the frequency of observations, and this was the temperature, today's October 2nd, you'd come up with a nice Gaussian-looking distribution, and the center of it would be something like a pleasant 20 degrees Celsius. It would decay off exponentially on the tails, right? And what would that mean? Of course, we know that we might have a day that is substantially colder or substantially warmer. But if this is a Gaussian distribution, we know that a day that is 20% warmer than the mean is certainly something we could experience. We know that a day that is twice the temperature of the mean is actually physically impossible, right? We're right now under the current climate, we cannot experience on October 2nd a day that is like 40 or 50 degrees Celsius, right? It goes beyond the physical constraints of the system. The reason I bring this up is that weather makes it so that this is a distribution and not just a fixed value. But a Gaussian distribution or a normal distribution says that this is a pretty well-behaved system, that you and I could take a pretty good guess. If we knew the average day, if we knew the average temperature of October 2nd, we'd have a pretty good idea of what today's temperature is going to be like. It might be a little hotter, it might be a little bit colder, but nobody would expect it to be 10 times hotter or 10 times colder, right? If we plot the distribution of landslide sizes, this is not what we see, okay? If you plot the distribution of landslide sizes, let me make it go off the chart so you can see how big it is, right? So we draw this in linear space. You draw the distribution like this. So you could say, okay, look, this is the average landslide size, right? I made it so it coincides with the average of this Gaussian, right? So I'd say, you look at, for the Gaussian, the average is also the mode, right? So the average is also the most commonly expected thing. When you look at the average for landslide size, what you observe is that it is not really representative of the distribution at all, right? So there's a whole bunch of landslides that are small. You observe that. But you also observe that the distribution is skewed so that there is a much longer tail to the right. What that means is it is not only possible but likely that I will observe a landslide that is 10 times or even 100 times the size of the average. okay? That is not something that we experience in daily temperatures. If you want to get an idea of this in your daily life, this plot here of landslide sizes is more like the plot of income distribution in America, right? We know that the average is, $60,000, $70,000 a year. We know that there's a bunch of people that are crowded to the left of that, but they're maybe making half. But we know also there's people making 10 times, 100 times, 1,000 times, and even 1,000,000 times the average, right? So the distribution of landslide sizes is more like the distribution of incomes in America. The average doesn't tell you anything about what's possible, and it's heavily skewed to the right, right? Toward potentially bigger slides. Now, because it's so skewed to the right, I want to look at it in a different way, right? So this is a histogram. Histograms are good for getting visuals, but I prefer to look at what we call like frequency magnitude plots, right? So what we're going to do now is plot the magnitude here, and we're going to plot the magnitude against this thing called n. And n is simply the number of things that are greater than equal to magnitude m. So what does that mean? It means that we're going to say that if I looked at the smallest event, we'd say 100% of events are bigger than the smallest event, right? And if you get to 0, that means that 0 events are greater than that biggest event. So we want to take this thing and we want to make it monotonic, right? And so what does that look like? If you drew a Gaussian distribution in this space, right, what it would look like is something like this, okay? So again, here's your average, and you see this distribution. It's symmetric about the average, right? And so the observations are dropping off very rapidly as you get larger than the average. If you were to make such a frequency magnitude plot in this space for this distribution, what would you see? It will look something like this, right? So again, you would see the tail, and it really highlights the tail as being a deviation, so things greater than the mean, right? Deviated to the right. However, you still maybe have a hard time envisioning this, especially when you have things that are like this, really widely distributed, covering orders of magnitude. It's hard to see all those orders of magnitude in a linear plot. So what we like to do is make a log-log plot, right? So if instead now I make this plot and I plot log of the magnitude and log of n, and I look at these things now, what do I see? So what the Gaussian distribution looks like in log-log space is something like this. It's a line of constant curvature. And what a power law looks like in log-log space is a straight line, right? The distribution of landslide magnitudes is a power law. And by power law, it means that the decay in size, as you get bigger and bigger, it decays as a power law function of the size. And whereas a Gaussian or other distributions have a thin tail, they have an exponential tail. The landslide distribution has a power law tail. Now, I should mention, there's always a cutoff, right? The maximum landslide that you can have on a mountain is a landslide that's the size of the entire mountain. So you can't observe, you're always going to have some critical cutoff beyond a certain size. And the smallest size has a cutoff too, whether that smallest size is a cutoff of what we're capable of measuring with pictures, or the size of a sand grain or something like that, right? There's going to be some small cutoff here, right? I wrote slop, I mean slope. Okay, so the thing about a power law, I had mentioned that we have this possibility of observing things that are 10 or even 100 times larger than the mean. Another way to say it is that there is no characteristic scale in a system like this. Now remember I told you last time, be careful of the word characteristic scale, right? It's a term that we use. Sometimes we mean the average. Sometimes we mean just sort of a reasonable guess. But in a system like this that has all of these orders of magnitude, it says that I can't tell you a single good number of how big a landslide will be in a system like this, okay? So the mean is not representative. The mean does not give you any good idea about the state of that system. So with the landslides, they're perched at critical. We have these fluctuations. We have the data we can observe as snapshots about how big they are using photographs, satellite images, field surveys, but they don't happen very frequently. We can't observe them happen, right? And so it's nice to have a model system where you can observe it dynamically, where you can stare at it and watch it as it evolves, right? And the one thing about lab experiments is that, of course, they're handy for a lot of reasons, but when we think about landscapes, when we shrink down space, we speed up time, right? So mountains build over millions of years. They're also kilometers, tens of kilometers, hundreds of kilometers in distance. If we make them in a sandbox in the lab, we can actually make things happen on the order of seconds and minutes, right? And so shrinking down space allows us to speed up time and observe things. Okay, so I'm going to leave that there for the resemblance. So now here's our simple system, right? Our simple system is a sandpile sitting on a table, right? So the idea, right, you can imagine that if you sit up here and you pour sand grains out, you know that when you pour them, what you're going to see is, you know, in the beginning, you make a little heap, the heap builds up, and at some point, the heap builds up to a critical angle, and beyond that, if you keep adding sand, the pile will grow in its size, but it will keep the slope, right? This slope, of course, is the critical angle. The pile will build until it's at the angle where the sand will fluidize and fail. One thing just to understand is that that critical angle that we observe at the macroscopic scale is actually related to what we call the internal friction angle, or an angle that the grains make at the local scale. Okay? So I've drawn these grains simply as spheres, but they can be other things, right? But imagine that you have a pile of grains, so you have one grain that is sitting in the pocket of these others. So that grain is stable in that pocket. And now imagine that you tilt those grains until the point where this grain rolls out. Right? The angle that that grain makes to the grains that it's resting on is also then the angle that you need to tilt it to in order to make the grain fall out of its pocket. Okay? So the idea here is that the critical angle that the pile builds to in the bulk is actually controlled by this internal friction angle, which is a geometric thing. Okay? Now, you could imagine that if these things were, if these things were cubes, angular cubes instead of spheres, that it might be different. You could imagine that if they were long grains of rice, that it would be different, right? So on the one hand, if I made a pile of sugar cubes or rice grains or sand, they would all build to a critical angle, and that critical angle that they build to would be this internal friction angle. On the other hand, that internal friction angle will be very different for all these different materials, okay? So there's this idea then about what happens once we build this pile to its critical angle. How does it behave if we keep adding sand to it? This is saying what happens if we have a system that by its nature is perched at critical and we drive it hard, right? Which is the argument that I was making is happening with the mountains and is happening with plate tectonics, right? So one thing that you need to understand with this threshold for critical is what happens beyond it, okay? So the basic idea is, let's say that we sit at this sand pile and we put in some flux of sand, QS in, right? So the flux of sand is just the rate, the number of grains per second that we're adding to the pile or something like that, right? And then let's say that we sit here with a bucket and we catch the number of grains per second that come out the bottom, right? So if this was like a pipe filled with water, the amount you put in here would be the amount that comes out there, right? And if you added water steadily at the top, water would come steadily out the bottom. You know, spoiler, that's not how the sand pile behaves, right? So we can add sand steadily to the pile, and what comes out at the bottom is highly intermittent. But what I want us to think about is just that the sand flux, the rate of sand or number of grains of sand per second that we can move, is proportional to the slope. And the way that it looks like in this critical scenario is that over a whole range of slopes, there is no sand flux that I can support. And then beyond a critical slope, what the threshold means is not that all of a sudden I transport infinite rates of sediment. It just says that beyond a critical slope, I start transporting sand grains, and the steeper the slope goes above critical, the faster the rate of transport I can sustain, right? So if I could take the sand pile and instantaneously tilt it to 80 degrees and release, what I would see is a very fast and high rate of sand transport, right? And if I could take it and magically tilt it instantaneously to 1 degree above critical, like 34 degrees or something, I would also see a transport rate of sand, but it would be lower, right? So there's no transport up to a critical slope. Above the critical slope, it's not that it's a switch, but it is a very rapid and highly nonlinear increase of transport rate with slope. So if you return back to the sand pile, the way that the sand pile is able to stay at critical, no matter how much sand I add to it, no matter the rate of sand I add to it, is because of this, right? If I add sand at a rate faster than the avalanches can occur, it will start flowing continuously. And it will actually build a slope that is slightly bigger than critical. It's just the fact that the transport rate of sand increases so rapidly with slope above critical that I'm never very far away. Even at really, really, really high fluxes, I'm still just slightly above critical. So if I were to write this out mathematically, it would say something like the transport rate of sediment is proportional to the slope minus critical raised to some power n, and that power n is greater than 1. Something big, right? Highly nonlinear. All right? And so this is kind of a generic transport equation. We see this kind of threshold transport equation in a lot of different systems. But this nonlinear transport equation, if you will, is kind of the mechanism or the reason why the pile is going to stay close to its critical state even when we drive it really hard. Okay? So we know that the sand pile is critical or close to critical. There's another important component here. Is that we say that it is self-organized. First of all, I'll explain what I mean by that just in words, which is that we didn't tell the pile, go find your critical slope. We didn't tune all the knobs of the experiments to do it. I'm basically telling you that you could add sand at the rate of 1 grain per year, or you could add sand at the rate of 1,000 grains a second. And what you would find is that no matter what you do, the pile is going to find itself at that critical slope, right? So the system perches itself at the critical point because of this nonlinearity in the transport, and it brings itself there on its own, regardless of the way that you drive it. And so we say that it is critical, being in this critical state between flowing and solid, and it is self-organized because it brought itself there. So what is that in contrast to, right? By the way, before I erase it, you guys see the mountain, the sand pile, the mountain, the sand pile? Yeah, just making sure. All right. So remember last time we drew our sort of canonical phase diagram, thermodynamic phase diagram for water, for example, right? So we said, okay, we're going to draw a phase diagram. We have temperature. We have pressure. Here we have solid, liquid, gas. And I had mentioned that there's this critical point right here in the phase diagram. Okay, I just kind of put it there and I let it sit, right? We're gonna, in these chalk talks, we're gonna keep coming back to this phase diagram. We're gonna keep coming back to that critical point. So you don't need to understand everything now. You know, it's just like, imagine like, there's like an ornate building, and every time you come back to it, you stop and look and you observe new details, right? So this is what we're gonna do here, right? So we're gonna take our first pass, or our second pass now, of this ornate building, right? So now, the thing about this critical point in the phase diagram is that here, right, the normal situation, right, is that we know that if I, you know, increase temperature with an ice cube, that I discontinuously cross a transition from solid to liquid, right? And if I increase temperature or pressure or decrease pressure along here, that I will discontinuously go from the liquid state to the gas state. But this critical state is special because in this critical state, nothing is discontinuous. This critical state in the phase diagram is marked by a spot where the water is somewhere between a liquid and a gas. It is simultaneously both and neither at the same time. So what do I mean by that? Well, you know, one thing we can use to differentiate these, you know, we talked about the energies, but we can also just talk about the densities of these states, right? And so, of course, the density of water does indeed change with temperature and pressure, but you see discontinuous changes in the density across these transitions, right? And if you were to look at the density, the local densities of liquid water in this regime, you would find that the density has a well-defined average and the local density is very little around that average, right? So if you have a cup of water sitting in this room, you could measure the bulk density, and if you could go in and measure the local densities, you would not really find any variation at all. The system is very well characterized by a bulk density that describes the average state of the liquid, right? At this critical point right here, the distribution of things like density, heat capacity, other quantities that we tend to associate with the different phases, that distribution is no longer Gaussian. That distribution is power law. So there is this special state in the water phase diagram where the material is simultaneously both liquid and gas, or neither liquid or gas, where the quantities of density or heat capacity are not well described by a single average, but rather have this power law-like behavior. And so this is a material that we would say at this critical point is mixed phases. Simultaneously, both phases are coexisting at once here. But if you notice something, it's a critical point, right? It's occurring at one place in, you know, so this is a two-dimensional graph, right? So there's an address for this critical point, right? You could say there is a certain critical temperature and critical pressure at which this special critical behavior happens. The system does not have this criticality anywhere else. It just has it at this critical point. So this is kind of the canonical critical point in phase transitions, right? And the idea that we have emergence of scale-free or power law behavior where we have no characteristic scale or characteristic average, the idea that we have mixed phases, is all happening here. But in this very classical canonical case, we have to tune the system to get there, right? So you imagine that you wanted to find this point experimentally, that you didn't know anything about it, right? You'd have to play around with temperature and pressure until maybe some point you happened to tune in like the right place on the radio dial and you find that. So this is critical, but this is not self-organized, right? This only happens under a very particular driving state of the system. The sandpile is critical, but it is self-organized. You don't need to do anything special. So the idea about self-organized criticality is that this sandpile is behaving like this critical point, but it does it without any special tuning or without needing to exist in any special place in phase space, okay? So the idea now that we're going to come back to is let us put, I want to choose some colors that makes this helpful for us to make a differentiation. So we're going to ask about the dynamics of the sandpile, right? Because I said it's useful to do experiments with a sandpile because we can observe it. So we put a steady flux in and we ask the question, what comes out for a critical system, okay? So if you sit there and you measure what comes out the bottom of the sandpile, let's just say that what we plot is a time series. So this is time, and this is, whoops, that should be out. This is the flux coming out. It could be grains per second that you're catching in a bucket or something like that, right? And so the flux in is easy, right? The flux in will just deliver at some constant low rate. That's what's coming in. What comes out? So it looks like this. Highly intermittent, right? Discrete events, actually. Sometimes they're clustered together, sometimes they're not. And you can ask a few things about this, right? So you could integrate the area under the curve of those discrete events and say that's a landslide, right? So you could ask what the magnitude of these landslide events is, right? In terms of number of grains or volume, right? So you could make a probability distribution of those landslide sizes if you wanted. Another thing you could do is you can ask questions like, how long do I need to wait between events of a certain magnitude, right? So if you ask the question, how long do I need to wait between events of a small magnitude, you would find that the waiting time is smaller. If you ask, how long do I have to wait between events of a larger magnitude, you would find that I have to wait a longer time, right? So you can ask questions like the average amount of time that you need to wait between events of a certain magnitude, or the average amount of time that, how that average changes with magnitude. All kinds of questions like this, okay? What you will get, maybe not surprisingly now, is that the answer to both is power laws, right? So for sure, if you plot this NM plot, right? So this is just the number of event avalanches that are greater than or equal to magnitude M, and this is just the magnitude of them M. So first thing is that you're going to have a power law distribution. It certainly has a maximum size. In this case, because it's an experiment, we can demonstrate that that maximum size is determined by the size of the sandpile. So the largest avalanche that you can have is an avalanche, what we call a slope clearing event. That takes the whole sandpile out, right? But there's a power law distribution of events smaller than that. But we can also ask the question about the waiting times, right? So we can make the same plot for the distribution of waiting times. And if you make the same plot for the distribution of waiting times, you will also find that it's a power law. And you will also find that the longest waiting time is associated with the largest avalanche, okay? So this is a critical system that is scale-free, save for the geometric constraints. And you can make it pretty easily by just driving the system at a steady rate. There's a couple interesting points about this, right? So first of all, again, no characteristic size, no characteristic waiting time, right? One thing that means then is this is sort of a hard to predict and anticipate system, right? If you wanted to ask me, what's the average typical landslide I need to worry about? Say, I don't know. If you were to ask me, what's the typical avalanche size I need to worry about on this sandpile, I'd say, I don't know. How long do I need to wait on average? I'd say I can give you an average, but it's not going to help you very much, right? So there's a problem with this, right? Which is it's a problem of predictability. Systems without a characteristic size are hard to anticipate or predict their dynamics in the future. There's another thing about them, though, which is a certain insensitivity. So what do I mean by that insensitivity? So far, I've said that we're driving the sandpile steadily, right? So let's instead now say that we're going to vary the flux in. And we're going to ask the question, how does the sandpile respond? If we start varying the way that we put energy into the system, how does that affect the energy coming out of the system or being transferred through the system, right? So one thing that we can do, the flux in against time. So we could say instead of making it constant like we did before, let's cycle it a little bit like this. Another thing that we could do if we wanted is say, let's make it, more intermittent. You could do something more elaborate if you wanted. You can put a whole bunch of different input signals into the sandpile up here, and you can sit here at the bottom and say, what are the consequences? If you look at the distribution of avalanche sizes or waiting times, you will very likely see no signature of this, okay? So on the one hand, these systems that are self-organized critical and perched at this threshold, they have no characteristic scale, they have these mixed phases, they're flowing intermittently and not flowing, and they're hard to predict, especially make any deterministic prediction. On the other hand, they're very robust to disturbances, at least over a given range, right? It's kind of like there's all this internal noise that's being generated within the system itself. And, it's like you go into a noisy, crowded room and you're quiet or you shout. Nobody can tell any damn bit of difference, right? This thing has a cacophony of frequencies and magnitudes that are all going on. And so if you kick it a little bit or you shake it a little bit, the system doesn't really care. So these are hard to predict and yet very robust dynamics. Now, obviously, this has its limits. We already talked about fluidizing soil with an earthquake. You took this sand pile and you just shake it with your hands and you can make it flow. You can make it respond in a deterministic way, right? So there are a range of frequencies and amplitudes of disturbances that this sand pile will care not about at all. It will be insensitive. But if driven beyond some certain range, then it will overwhelm the internal noise and the system will respond in some kind of deterministic way. It turns out to be quite subtle to pick apart which kinds of disturbances this system's basically going to filter out or buffer and which kind of disturbances it's going to respond to. We actually leave that to a later chalk talk, okay? If you think about this, coming back to the mountain range, which I, did away with, so I'll just draw it here, right? But if you just think about the mountain range with the landsliding happening on it, we know that, it's raining on these mountains. We know that there are earthquakes that are shaking these mountains. We know that there's freezing and thawing and all kinds of things happening. And there's a whole bunch of disturbances that are acting on these mountains, and the mountains care not, and they don't respond in any really predictable way. But then we know that there are certain large enough events, or events maybe that happen at just the right time, right? So that can have a very direct deterministic result and make the landslide get triggered, right? And so just like the sand pile, I want you to understand that these mountains being perched at critical means that there's a whole bunch of little shocks that they can absorb and have no response to at all. But it can be quite difficult to predict that there will be certain kinds of shocks that they will have a catastrophic response to. Sometimes it's just a matter of frequency and size of the disturbance. And sometimes it's a matter of history, that the system has absorbed a whole bunch of shocks, but it's also evolved itself closer to its internal critical state. So one little shock that's even smaller than the one that happened before, but is just enough to knock it over the edge, and it goes, right? So coming back to the point about plate tectonics, I had mentioned this idea, right, that we also have, that the plates are also in this critical state. And so what do I mean by that? So let's imagine that this is a fault, right? So we have two plates that are sliding past each other. And so, right, so this is a plate, this is a plate. Let's say that they're moving this way. And so there's a frictional interface, right? We'll talk a little bit about some of these details later. But for now, we're just going to say, right, there's a frictional interface from these plates. And we know, of course, the fact that there are earthquakes means that most of the time there isn't. What does that mean going on here, right? Well, these plates are being driven from below by the mantle convecting, which means that they want to drift around and move. But at this interface, they get locked because there's friction, right? So they're being driven from below and they're being loaded against each other, but they're locked and they're not doing anything and we're living happily without an earthquake. And then we know that at some point, the plates slip. They overcome the internal resistance, right? The stress is built up enough and that thing goes and we get an earthquake, right? So, first of all, you guys probably know we have to give props. The power law earthquake frequency magnitude plot is like the OG power law plot of critical phenomena, right? In other words, people going and measuring the magnitude distribution, the moment magnitude distribution as they call it, of earthquakes, and finding out that they are power law over many, many, many orders of magnitude. Realizing from doing experiments at very small scales that you can produce that kind of behavior from, rocks being put together, right? They've known this long before we were playing around with sandpiles and spin glass models and whatever else things that physicists and geophysicists like, right? So, but I'm not going to presume that anybody here has any knowledge of that. And so there's someone here who has a lot of knowledge of that, David Goldsby. So I embarrass myself when I talk about experts in front of here. But I'm going to talk about just the dynamical perspectives that are related to sandpile and other things, right? So one thing that you can observe, that we can observe actually from field data, but we can also observe from experiments, is that you can make plots of things. Like, let's say that you're measuring the stress, the shear stress between these two boundaries as they're being loaded, right? So what you will see is that over time that the stress is getting built up. They're being driven either in an experiment, we're driving them, trying to force them to move, or in nature by mantle convection ultimately that's dragging on the plates and trying to get them to move. What you can observe is that the stress builds up, and then when an earthquake happens, it rapidly drops. Stress builds up again, you can get a drop, right? And so there's this intermittent thing happening, right? And so one way for us, one simple measure of the magnitude of an earthquake will just be the stress drop associated with the slip of the plates, right? So this is like the stress that gets dissipated by the earthquake happening. If you want to think of it in terms of motion, right? So let's just say that this is velocity. So in an experiment, when you do this, you basically drive the plates at a constant velocity, and then they slip, right? So if you're doing this, what that would look like is, say, that you're driving them at some really slow velocity like this, and then these are associated with, right, there's these, when the slip happens, they speed up a lot, right? So you could look at something like the speed of slip that's happening at the point where these plates are sliding, okay? So, I mentioned this already. I should have just left the plot here. We know that the NM plot, the frequency magnitude plot for earthquakes, is power law. Like I told you, it's the original power law. The cutoff here for earthquakes in real life, right? I mean, what do we currently have? Magnitude almost 10, 9.5 or something like that, is a terrifyingly large. There is a limit, by the way. Earthquakes happen along faults, and the largest earthquake that you could have would be slip that happens simultaneously across the entire length of a fault, right? So any fault that has an earthquake does have a finite size, a maximum at which that determines the magnitude of that slip, right? But you could also plot something like, the waiting times between events of a given magnitude. I don't feel like drawing more plots. If I drew the plot of the waiting times, it would also be power law. We know that. And the way to think about this, though, is just like the sandpile. If you said that there's a velocity or a speed of slip here that's proportional to the friction along the fault minus some critical value that's associated with slip or failure, right? Raised to the n of some nonlinear power, right? In other words, what I want you to understand is the same idea that when you drive the system past critical, that it responds very rapidly. But as it responds really rapidly and it drops its stress, it brings it right back toward that critical point, right? So the fault is sitting there. It has this highly nonlinear thing, right? So what you understand is even if you drove the thing really hard, you're not going to keep it in a state that's too far away from critical because of that nonlinearity, right? So the system is perched at critical. It is self-organized there. And just like the landslides and just like the sand piles, we have no characteristic size of earthquakes. And we have this weird paradox of being hard to predict, but statistically being very robust, right? That's just sort of the general characteristic of these critical systems. Maybe another system that is less obvious, which is why I think it's fun to talk about in this context, is rivers. Okay, so if I draw a river, I want us to think about it a little bit in context. So imagine we have a nice sweeping river that's starting in the distance. I'm trying to draw it in perspective coming into the page. Okay, and now here we draw the cross section, right? So the river is made of particles that line the channel. An alluvial river is a river where the bed and banks are made by particles that the river itself moved, right? And so this river system, if we zoom in on it, what I want us to focus on is there's a channel cross section that looks something like this. I'll draw the water surface. And I'll remind you that anytime I draw an upside down triangle with 3 little lines, that means a free surface of water, okay? And so the flow in this system is like this. So coming down toward you, if I wanted to draw a velocity profile here, right? There's a velocity profile laterally across the channel. Okay, so at the walls, the flow is slow. There's no slip. Furthest from the walls in the middle of the channel, the flow is the fastest. And so you can think of it as like a half pipe, right? Water running down this channel. Okay, so the idea is that, let's imagine a scenario where the river channel is like a canal. What do I mean by that? So the river channel is a channel that is filled to the top of its banks. It's lined with loose material, but with a canal, it's by design. The fluid stress, sigma, is less than the critical stress to move a particle. Okay, this is how we design canals. We know that there's particles sitting on the bottom. We know that there's going to be a critical fluid stress beyond which you'll pick the particle up and move it. And so when you design a canal, you design it so that you have the maximum amount of water flowing without eroding the thing. Right? So, what happens if you raise the water level? So to answer that question, we have to talk a little bit about this critical, right? So let's draw this in profile. So now here's our river channel from the side. Here's the water level. And of course, there's also a vertical velocity profile. Looks like this. And there's a particle that is sitting on the bed. There's a particle that is sitting on the bed. making an angle with the particles it's resting on, its internal friction angle. And in the case of the fluid, what the fluid does is it exerts a stress, sigma, associated with drag and lift on this particle, right? And when the drag and lift acting on that particle exceeds the friction associated with the particle that it makes with the bed, the particle gets moved, okay? That's the threshold of motion. And so in this scenario of the canal, right, so this critical is the critical defined by rocking a grain out of its pocket by the lift and drag forces that act on it, okay? So back to the canal now. Let's say that something catastrophic happens and the water level in the canal gets raised. And the water level in the canal gets raised to a sufficient depth that now there are portions of the river channel where the fluid stress is greater than critical, right? So there are now portions of the river channel on the banks where the flow is sufficiently strong to pick up the particles and move them. If that were to happen, remember these banks are made of particles. These particles are heavy, so the particles get picked up. They get transported downstream into the page, but they also get transported by gravity down into the center of the channel. What is going to happen is that these banks are going to erode, okay? So if you drive the river system to a stress that is large enough that you excite transport on the riverbanks will erode. And if the riverbanks erode, this channel will widen, right? And the channel will widen until it brings itself right back to the spot where the stress is equal to critical, right? So a river channel is free to adjust its width and its depth to an imposed stress. And the principle that I want to show you here is that the river is actually like a sandpile. It's like a sandpile on a lower slope because you have fluid drag and lift force on top of gravity, right? But the point is that if I drive a river system too hard by increasing the discharge, increasing the flooding, the river is going to widen, and as it widens, it's going to drop the depth and drop the fluid stress until it brings itself back to being in the vicinity of that critical point. And not surprisingly, I'm not doing any derivations, you probably realize this by now, but one thing we know from studies of sediment transport is that the sediment flux driven by lift and drag forces coming from a shearing fluid flow goes like the fluid stress minus critical to some power n that is much greater than 1, right? So again, it's not that you can't drive the system far from critical, or you can't drive it above critical. It just says that you can't drive it too far above critical. So anything that happens that increases the sediment flux by a lot is going to cause erosion a lot, which is going to relax the system back toward critical, okay? So just like other problems, this makes prediction of some aspects of river channels hard. It makes prediction hard because I'm saying that you are always hanging out in the vicinity of critical. So the fluid stress during floods is always not very far from critical, but it might be slightly above, it might be slightly below, and because this is such a nonlinear function, if it's slightly above, you could have a lot of sediment transport, right? So it says that you need to know, you need to have exquisite knowledge of what the fluid stress is. You also need to have exquisite knowledge of what the threshold is, right? So you could be off in your estimate of threshold by 10%, and that could be the difference between no transport at all and tons of erosion, right? Because of how strong this nonlinearity is, okay? So that is the thing that makes prediction hard. On the other hand, just like the sandpile, one thing we know from the field, but really, especially from laboratory experiments, is that river channel geometry is not that sensitive to how this forcing is delivered, right? So in some rivers, if you just think about the forcing for us will be the water discharge, right? So it rains. You can think of this as water discharge. You could just think of it as rainfall. It doesn't really matter, right? So in some very large rivers like the Mississippi or the Amazon, they're integrating over so much drainage area that they're seasonal. So if you plot the amount of rainfall or the amount of water flowing in the river, there's going to be some very regular long wavelength delivery, okay? So they're forced slowly and seasonally. There are other systems like in the tropics that are prone to hurricanes, or in the desert where it might not rain for 20 years and then it rains a lot, where the driving of the system looks like this. What you will find, though, is that the river channels adjust their geometry to be in vicinity of threshold, and they sort of integrate over and buffer against all of this messiness. So it highlights this idea that because of this nonlinearity, which brings the river systems right back to critical, they're pretty noisy, they're hard to predict, but there are certain properties that are very robust to disturbances, right? And so that means that there's some hope of understanding the physics of the system even when it's variably driven by intermittent driving out in nature, right? And so the idea that I want to bring back together, right, is that when I say that the world is a sandpile, that I want you to understand that it's a collection of tectonic plates which are all perched at critical, fluctuating in landslides, or fluctuating in earthquakes. That criticality also produces mountains that themselves are perched at critical, with power law distributions of landslides and intermittency and unpredictability, but robustness. And then that there are river channels that are cutting into those mountains that are also at the threshold of motion, that are also perched in their critical state, and they'll be there essentially no matter what you do. And so they're all strongly driven systems with thresholds, and that makes them self-organized critical and perched in this place, right? And I'll remind you that there's no characteristic scale in a lot of these systems in terms of their dynamics, but there's this robust statistical behavior that makes them fairly insensitive to at least a range of forcings, but sometimes exquisitely sensitive to some forcings in a way that's very hard to predict. And so one of the things that we're going to do in the next Chalk Talks is unpack some of these comments in more detail, but that's all I got for today. Thanks. Any questions? Yeah, okay.
I was wondering about the, so essentially the way, and this is going to sound very naive, the essential way in which I understand mountains is that you have a competition between erosional processes that take material off of the mountain slopes.
Yeah.
And there's also uplift.
Yes.
But I was wondering if in that competition, wouldn't it make more sense to think of mountains as, like, essentially they get to a certain height as you're uplifting, and then at some point the rock starts to yield in the mountains because these columns just are taking so much load that they cannot withstand just more uplift and still maintain their shape. Wouldn't you say that that is also a significant process?
Yeah, so I'll try to repeat the question just because of the mic, but succinctly, and then we can go from there, right? So the question is about erosion and uplift and the balance, and you're okay with that. But your point is, isn't the balance of erosion and uplift, isn't the erosion part just that the rock gets so steep that it's a rock losing its competence and breaking apart question? And I was making it more like a landslide, soily kind of question, right? And I chose landslides because they're obvious. So there's a lot of complicated geologic factors, some of which I'm going to get to, though, in Soft Earth Chalk Talk number 4. But there are places on the Earth, even steep places, where the mountains are covered in soil. You know, we were in the San Gabriel Mountains in California, which are some of the most rapidly uplifting mountains on the planet, and they're still covered in soil. So there are mountains that are covered in loose granular material. There's rock at depth, but on the surface it's granular. And in those cases, they're definitively landsliding, right? This is also true in a lot of places in the Himalaya, where they're going up a centimeter a year, and there's still places where it's just massive landslides. But there are plenty of other places where steep and rapidly uplifting mountains are not soil mantled at all. In which case now the failure criterion that you're talking about is the internal friction or breakage threshold for a solid rock. Now conceptually they're the same, right? So the slopes will get steeper, but if you make a steep enough cliff, right? At some point you make a steep enough cliff and the tensile stress ripping on the rock apart is going to cause it to crack and break. So all of them will have a threshold and a sufficient stress at which they're going to start to fall apart. In the case of a soil mantled landscape where I can say that they're landslides, I can make an analogy to the sandpile that's pretty direct, and I can be like, oh, the angle's like 30, 40 degrees. What we tend to see is that if either the place is too cold or too dry or too whatever to actually weather rock and make soil, then you end up with bare rock and the critical slope ends up being steeper. So it's still the same idea that and you get rock falls, right? You're still going to be perched at critical and you're still going to have rock breaking and then shattering. And it's going to be perched at whatever slope that it needs to meet that criterion. But it's harder to draw a direct connection to the sandpile than it is with the soil. So I talked about soil mantled landslides. I would say climate and geology dictate whether the steep mountains are covered in soil and are landsliding or whether they're, bare rock. So yeah, it's a good and appropriate question, but I intentionally skipped the bare rock part just to make the analogy cleaner. Yeah.
I'm sort of still not struggling, but trying to understand the idea that the criticality of all these systems is insensitive to a lot of various factors that you're talking about, mainly the forcing. Right?
Yeah.
But then I'm also thinking of other systems that exhibits such failure events like snow avalanches or glaciers breaking off and creating icebergs and so on and so forth. A lot of those factors, there has to be some influence of the fact that it's ice as opposed to a sand grain or a little bit of soil that's in rivers and so on and so forth. So would you still see insensitivity to things like adhesion or frictional factors and so on and so forth?
So I'm going to keep saying this so the first cheap out is we will talk about these things when we get to the 7 and 8, which is details don't matter and details do matter. But I think one way to think about it, right, is let's think of a simpler system, right? So we look at the cup on the table, right? And I apply this forcing, I apply a bigger forcing, I apply a smaller forcing. I'm basically like, not much, not much. And at some point when the cup is here, right, I can apply the same forcing, modest forcing, and it falls off, right? So the one thing to understand, first of all, and bringing up the cup is an important example because these systems all have history, right? So they're being driven, they have a critical point, right? What I want you to understand is that they have this internal noise to them on their own because of this criticality that even if you drive them perfectly steadily, they're acting like a system that's being driven wildly, right? You could drive a critical system very, very constantly and it's going to look like it's turbulent, right? It's going to look like it's like, that you're doing wild stuff to it. So the first part I want you to understand is just that it kind of makes sense that these systems have all this whirling, swirling chaos, even when they're driven steadily, that you add a little bit of chaos and it's not going to do much. But what you also understand is if you add just a little bit of forcing or chaos at just the right moment, these systems are getting driven. When they go above critical, they fail. And when they fail, they drop below critical and then they build up again, right? And so there's going to be portions in their trajectory where they're going to be really insensitive to what you're doing. And then there's going to be portions in their trajectory where they're exquisitely sensitive to the last thing that happened, right? Snow avalanches are power law. Snow avalanches famously can be triggered by the smallest touch of a skier or a hiker that's on there, but other times can be stable for an entire season of people tramping all over it, right? And so what I mean is qualitatively, it's all the same. These are systems that are critical and they can experience no response to disturbances or disproportionately large responses to very small disturbances. Those are both hallmarks of a critical system. I would say that for now, the best way to think about your question, not the only way, but one way to think about your question is what it says about critical, right? So a system that gets shaken by an earthquake like soil and it doesn't fail actually has its critical point changed. It has the critical threshold changed because you reconfigured it. We're going to talk about that in lecture 4, right? The snow that is fresh powder is very different from the snow that has been sitting there experiencing freeze and thaw and getting consolidated and turning more to block ice, right? The dry powder snow behaves a lot like a sand pile. The consolidated snow behaves more like rock in like slab detachment. It's changing, it's critical as it's being driven, right? And so the simplest case, like it's true that I did this very cartoon version right now where I basically acted like critical is just a fixed quantity because that's the simplest way to think about it. But what we're going to start talking about is in these driven systems is the way that critical itself is actually like a state parameter. That it is telling you something about the state of the system and it evolves as the system is driven. But all of these dynamics I talk about are what you get even if that's constant. So if you start letting that vary, it's only going to get more complicated than the framework I've presented now. Is that a okay enough for now answer? Okay. Okay. Yeah, back there.
Thank you for the talk.
Yeah.
So I was really interested in what you were talking about, how these systems are dependent on the history.
Yeah.
And I think a lot about that as a biologist,
Uh-huh.
because of how biological systems are dependent upon the buildup of information in the genetic code,
Yeah.
as well as sort of like the sudden erasure of that information in like a large scale population death event. And
Yeah.
so I was curious, are there ways that, or like certain metrics that you use to study the history of the geophysical systems?
That's a great question. I mean, part of this is feel bad. I'm going to punt because it's like stay tuned for later lectures because we are going to talk about the first. I'll step back and say that one of the things that's happening is I'm trying to set up frameworks and ways of thinking, but also basically set up a bunch of questions so that we can go examine them, but you'll have the context. So we will talk about that in future lectures, but only for very specific systems, right? So we're not going to give you a metric that is generic enough that you could use it for like a biological system or a chemical system or something like that. But there is, and it's for us when we think about materials, right? So a lot of this is, what's implicit or explicit in a lot of this is that we're talking about materials, right? So in materials, one of the things that we try to do is look at the structure of the constituent grains or particles or molecules or whatever they are and understand that that arrangement of those particles that make up the material encodes in it a memory of the forcing, right? And so, for us, it could be that, a simple example would be imagine that you have a bunch of rice grains just to make it really apparent, right? So let's imagine that you have a bunch of rice grains. So I just picked something really elongated so it's obvious, right? And they're all randomly oriented in the beginning and then I shear them. So what's going to happen is that you'll see them eventually aligned like this, right? And we will know, I'm just making a very cartoonishly simple example for this one, but you would look at that structure and you would say, when I just poured the rice out, it was not arranged in that way. And there must have been a history of shearing that allowed these grains to line themselves up. Now you can go from this to more elaborate structures. And so one thing that we see in materials is that the more that you excite them and shake them or shear them, as long as you don't fluidize them, they encode structures that evolve and get more complex and bigger over time. You start to get networked arrangements of particles, and you can measure that in the alignments, in the angles, and other more sophisticated measures. But If you shake it to the point that it fluidizes, you lose all that structure and it's gone. And that's like your question, right? And so just like you're encoding all of this, you're encoding all these mutations in this population that you might see, but if you wipe them all out and start it over, that's the slope clearing event and you've erased history. And so essentially when these systems are below critical, they encode in the arrangement and structure of the particles their history of being forced. But once they hit critical and they fail, you've reset the entire system and that memory is gone. But we will describe that in more detail later. Yeah, okay.
You stopped short of drawing that log n versus log waiting time versus log m plot. Would it be just a reflection about the horizontal axis for this graph, like the waiting time?
For which system? I mean, it's the same for all of them.
Yeah.
It's just another power law.
But,
in other words, the amount of time you wait between small events is short, and the amount of time you wait between big events is long.
yeah.
But that dependence is power law rather than something, right?
So if it's a large event, then you would have to wait for a longer time. So it
Correct.
would be an increasing function.
Oh yeah, but this is a 1 minus cumulative. When I draw the frequency magnitude plot, the number greater than m, right? And so, in a cumulative plot, it goes like this.
Yeah.
I didn't mention cumulative because it's cumulative then 1 minus cumulative, but this is like a 1 minus cumulative plot. That's the way to think about it. Yeah. All right. Thank you, everybody. That was great. See you next week, hopefully. I mean, I'll be here, but I hope you'll be here.